Thank you for the introduction. Today I'm presenting our paper on FedTM, Memory and Communication Efficient Federated Learning with Tsetlin Machine. So this is the outline of my presentation. So first I will introduce what federated learning is, followed by the motivation and applications of federated learning. And I will also describe the challenges faced by current federated learning methods, and also give an overview of our proposed solution, FedTM, which aims to resolve these challenges. And also I will share our findings of FedTM's ability to outperform existing baselines in terms of both performance and efficiency. So firstly, what is federated learning? Federated learning is a machine learning approach that facilitates model training across a network of decentralized devices. And this eliminates the need to share sensitive data with a central server. So in contrast with traditional centralized approaches, so where data is transmitted to a central server for model training, federated learning brings the model training to your device, and this ensures that your personal data remains on your own devices. So the motivation behind federated learning comes from the need to address the challenges of traditional centralized machine learning, especially data privacy. So because federated learning ensures that your sensitive data remains on the edge and you never leave your devices. So with the increasing number of network connecting devices, federated learning ability to train models on devices while preserving data privacy and security makes it well suited for various practical applications. So some examples of federated learning in real life examples would be in healthcare, where implantable sensors enable continuous monitoring and personalized treatment recommendation. And also, for example, in your smart home devices, it can help to optimize your energy consumption and also improve security measures, all while safeguarding your user privacy. So the most widely adopted federated learning technique is Fed averaging. So in Fed averaging, each local device trains a neural network model as the base model. So at each communication round, the client does gradient descent for a specified number of epoch on the current model. And after training the current model, they will upload the parameters to the server. And at the server, the server will compute the weighted average of the parameters based on the data sizes, and they'll obtain the new aggregated parameters, which will then be downloaded to the clients, and the clients will then retrain the new model with their local data. And this iterative process continues until a specified condition is met. For example, reaching a predefined number of communication rounds or achieving a certain performance threshold. So as what was mentioned earlier, the typical federated learning process uses deep neural networks, and this can be computationally expensive, especially for edge devices with limited processing power and limited memory and storage capacity. So because of these computational limitations of edge devices such as IoT devices, this can impede the ability of model training on device and leading to training inefficiency and slower convergence. And also, federated learning requires uploading and downloading large amount of parameters for numerous number of communication rounds. So because of this low bandwidth of edge devices, transmitting this large number of parameters across the network results in a huge communication bottleneck. Also, unlike centralized machine learning, where the data is shared at a central server before aggregation, federated learning requires each client to train an individual model on their local devices. So since the data collected by different clients vary differently, and it's not guaranteed that all clients will collect the same data distribution, so the model trained with different local data can lead to a discrepancy between the weights of the local model and the global model. So this results in the inability of the federated learning model to converge, and therefore data heterogeneity on having non-ID data is one of the main challenges in federated learning. So to summarize, the main challenges of federated learning is to have to deal with the limited computational resources of edge devices, the communication bottleneck, and data heterogeneity. So therefore, we propose FedTM, which is based on the Tsetlin machine, and it offers a substantial reduction in parameters through logic-based formulation and beat-based communicated parameters between the server and the client. And lastly, we also recorded the memory cost. So we recorded the average runtime memory for training each client during a communication round and the memory storage of the parameters stored on each client devices. So now I'll show the results for the IID data. So if you can see from from the table here, if you see FedTM, it outperforms by FL up down and by FL ML on all data sets. But also you can notice that FedTM also has a slight performance difference from the Fed averaging CNN and BiFL full, which transmit the full 32-bit parameters. So this slight difference can be if you look at the trade-off between the test accuracy and efficiency, right, this slight difference can be justified, especially if you use edge devices with limited computational resources. So now if we look at the convergence of the algorithms, so to compare the convergence of the algorithms, we look at the test accuracy at each communication round. So as we can see here, FedTM achieves peak accuracy within 30 communication rounds. And when compared to BiFL, BiML, and BiFL up-down, FedTM achieves higher accuracy and has significantly less fluctuation during training, which means that at any point in time after the first few communication round, if you stop federated learning training, FedTM ensures convergence compared to BiFL, BiML, where the training fluctuates and convergence at any point in time is not guaranteed. So now we look at the performance of the non-ID data. So if you can see here, when there's low heterogeneity, all algorithms perform relatively similar in comparison with their ID data distribution. But when there is high data heterogeneity, the performance of other baseline methods diverges more significantly from the ID setting compared to FedTM. And also FedTM outperforms all of the baselines in terms of non-ID data. So now if we were to look at the communication cost, if you look at the trade-off between efficiency and accuracy, FedTM outperforms all the baseline. And we can also see that FedTM provides the optimal solution for non-ID data in terms of communication cost and performance. And lastly, because model storage size and runtime memory is an important consideration for edge devices, we can see here that FedTM uses lower memory storage than Fed averaging CNN and BiFL full, which uses real valued weights for training. And also FedTM provides better performance in the non-ID setting. However, if you notice that FedTM also uses slightly more storage memory than BiFL up-down and BiFL ML compared to FedTM, and it comes at the significant trade-off in terms of reduced accuracy. So especially in the non-ID setting, you can see that FedTM performs at least 3 times better than BiFL up-down and BiFL ML. And in terms of average runtime memory, FedTM has lower runtime memory usage per client compared to BiFL. And overall, looking at the runtime memory and the storage costs, the results suggest that FedTM is not only storage efficient, but is also memory efficient. So in conclusion, by ensuring we introduced FedTM, which is a new framework that utilizes the Tsetlin machine to significantly reduce communication costs while also maintaining good performance. And our proposed solution outperforms all baselines, especially for the non-ID setting, and also outperforms the state-of-the-art in all federated learning settings, as well as reducing communication costs and runtime memory. So while the experiments that we showed has promising results, we only evaluated it with image data sets. So we plan to extend the capabilities to constrained devices as well as to other domains such as audio and natural language processing to prove its generality. And lastly, FedTM demonstrates significant reduction in communication and memory costs while also maintaining good performance, making it a promising solution for efficient FL. Thank you.
Very good news. Anatoly, please.
Thank you very much. Very interesting. And my question is that by default, we assume that the federated AM work with the homogeneous models,
yeah.
right? So exactly the same architecture, exactly the same number of neurons and the layers. So in your experiments with the TM, whether you used the same TM, so the same structure, and have you tried to do federated learning with the heterogeneous Tsetlin machines?
Okay, so for our experiments, we use homogeneous, like the CNN, same number of neural networks, same number of parameters, everything. And we also plan to extend it to different TM structures per clients, yeah, to handle the non-ID data better. Yeah, thank you.
Right, thank you. More questions? Jesse. Yeah.
Sorry, it's not really a question, but now that you said it's image processing you were doing, I imagine when you put CTM, you meant convolutional.
Yeah, I did.
Thank you. Very nice. Right. Everybody should be on alert. Right. Any more questions or comments, observations? Right. My perhaps not so much a question, but in terms of communication, sometimes what we're seeking is to not to make them too regular, perhaps not to sort of sampling communications, but rather more like event-driven type of communications. Is there potential here to make them more event or classification-based communications rather than sort of broadcasting or multicasting? Yeah.
So we plan to extend it to one-shot federated learning. So you only do communication just once. So that is what we thought of also. So that's a good input. Yeah, so we're still working on that now.
Right. Thank you very much. Right. If there are no more questions, well, let's thank Shannon very much again.